Welcome back, everyone. This section is about types, the type system in F Sharp. Now, as a matter of fact, type system in F Sharp is quite a comprehensive topic, an area which requires a number of discussions because it's quite horizontally spread. So what I'll do is I'll discuss this in at least three or maybe four, five parts. This is part one of the discussion, and currently I'm discussing essentially three things: type aliasing, records, and discriminated unions. So once again, the sample code where I've tried to highlight everything is committed on GitHub. You can always check out the code, and you can go through the blog where I've tried to cover as much as I could. Now, let's begin with type aliasing, what it is. Now, I'll copy these two examples and go to work area again. Now, this type a name and then followed by a type name which already exists is an alternate substitute name that you can create for any type. On the blog, I've also shown these examples, so I'll copy these. So if email is a synonym for string, width is a synonym for an unsigned int, and so on and so forth. A rectangle is a synonym for width into width, which is, if you recall, that's how the signatures for tuples work. This fancy looking thing is a signature for a function which takes anything because it's a generic parameter and returns anything. So you can create alternate project specific, domain specific, need specific name for your types instead of using the generic names like int and so on and so forth, or string, or a list of int, or an option, int option, and so on and so forth. You can use your friendly names, and this technique is only to bring some kind of uniformity for types names. This technique doesn't solve various other problems that are there with types, which we will discuss as we move forward. Type system offers various answers, and not just type system plus certain techniques that you can use to overcome a lot of problems that are there with business applications. On the surface, type aliasing seems it's going to solve you a lot of problems, but that's not true. It's just giving alternate names, either for you like certain names, or to have uniformity across the project. So for example, you may say type number or num equals to int, and you can create a function let add to x, which is of type num, equals to x plus 2. That's it. So if you look at this function, it says, this is odd, why is it saying so this is a bit funny thing, but never mind. So you can say that x is of type num, but behind the scenes is just an integer, so it just doesn't make a difference. Technically speaking, it just doesn't make a difference. Now let's start with and I've also said that two issues. One, I already pointed out that there are issues which you cannot solve with creating alternate names for types. There are issues that you have to solve in a completely different way. The other is that alias names are not available outside F Sharp. It's only available within your F Sharp project, and so on and so forth. All right. Now let's start with records. Once again, I'm just going to copy this bit. And here. So records are like tuples. Records are for grouping of data, but tuples and records are fundamentally different in many ways. So a record is created or defined in like this. You give it a name, and these are record members. You give the name of a member, colon, the type of the member, followed by the next member, and so on and so forth. And there is an alternate syntax allowed. For example, you can say age, which is, let's say, int. You can also have things spread over multiple lines where semicolons are optional. You can have semicolons in this case, but which is not needed. So if you spread a record over multiple lines, it's not needed. If the record is not spread over multiple lines, you have to use semicolon to separate the members of a record. And this record has two members. So if you roll your mouse over the record type, you can see first, which is a string, and then last, which is also a string in this example. And we have created a type called full name. Now, how do you construct a value of type full name? You have to simply say let full name equals to, and then comes the values for the members of the record. First equals to x semicolon, second equals to y. What did I miss? Oh, last, not second. Now, the type, once again, F-sharp's type inference comes into picture, and I didn't declare it like this because I created a record type value, and F-sharp compiler couldn't use all sorts of intelligence to figure out that, because I have specified first and last, which is this. This is full name. But you will run into situations where there are conflicts and so on and so forth. So I'll talk about that later. So practically you can also do this. You are forcing a type as opposed to letting the compiler decide the type. And you may even have nested records. For example, you may have type student equals to name of the student, which is of type full name, and age of the student, which is of type int. And here you say let student equals to the first thing, which in itself is a record. So you will say name equals to whatever, and age equals to, let's say, 10. Why am I doing colons? And here you can actually copy this bit. So here you have a record which is nested. Both these records are defined here and then created here. Now, when you define a record in this fashion, it's immutable, meaning thereby that not only is this immutable because you have not created a mutable binding, the members of the records are also immutable. Once this value is created, there is absolutely nothing you can do with it, and which is the recommended way. Once you always follow this, stick to this philosophy as much as you can. There are cases where you need to get down to imperative techniques and mutation and so on and so forth, but those are few cases, and that's for another discussion. This technique, this method of defining records and creating values for records is all resulting into completely end-to-end immutable values. You cannot touch it. So it's a frequent requirement is a value is created, but you need to change a part of it. So you don't really change a part of it. What you do is create a copy of it and then make those changes in the copy. So for example, you may say let new fname equals to fname with whatever you need to change, and this is what I've also described here. Okay, sorry, you don't need this. So what I'm asking here is that create me create for me a copy of f name, which we created here, full name, which is x as first name, y as last name. I'll get rid of this. Let me just comment it out. Ignore it. So new f name is the old f name. Create a copy of it, and before that copy is returned, change the value of last. So if we do print fn, again I'm using a because a allows me to print nearly everything without too much jazz, and new name, and if we run it, we see that first the values were x and y, and now that the record has gone through a change, just to clarify my point, let me print after this change is done. Let me print the f name again. So you can see x and y here and x and y here. F name, the value f name remains intact. The last name, the last part of the f name is changed, and that is what new f name becomes as this. So this technique is called copy and update record expression. Now, as I said, if you define your records like this and then you define your values like this, you cannot mutate it. So I have given an example on the blog that how can you create mutable records and how can you change the value. But once again, you have to have very strong reasons to do it. Extremely strongly recommending not to follow this path. This is just not needed. Now, for those of you who come from C# and perhaps Java background, they may see or they may feel that records are like classes, and you will not be wrong in thinking something on such a line that records are classes. As a matter of fact, records do get compiled down to classes, but records, before they are compiled, there's a lot of magic or garnishing that happens before those classes are compiled out. And this is I have tried to explain the key differences. First thing first, with classes you have to deal with constructors. There are no constructors with records. With records, this kind of construction is known as record expression. So you always create values for records via record expressions. The constructors are never involved. Secondly, classes allow fields, properties, getters, setters. With the record, there are just fields. So this field and this field and so on and so forth. Another big key difference, and this is applicable both in C# and Java, is the equality of objects in C# and Java is based on reference equality, which is if you have two instances of full name and if you do equals to comparison, you are essentially checking for the equality of reference. In other words, are those references pointing to the same thing? You can override this behavior. There are all sorts of tricks and override, equatable and whatnot. However, it's a typical issue that in the object-oriented world, equality means equality, referential equality. Records, on the other side, are implicitly all the extra hard work, all the extra weightlifting compiler does for you. When records are compiled, they are compiled down with structural equality baked into them. So whenever you compare two records, the values of the members is what is compared, not the references. And this is important because a lot of times you need value comparison. Not a lot of times, mostly when you are writing business layer, the value comparison is what you are interested in. As a matter of fact, when you are in the business layer, you don't care about references and the equality of the references. Those are the areas where you are especially dealing with high performance layers, algo-centric layers. That's not business layer. Now this is an example of creating a record with members. So I'll quickly give you another example of this. Now this is a record called employee, which has three fields: name, which is name, which is full name type; age, which is int; employee ID, which is string. And if you have created static members for classes in C# or Java, this is a static member for the type employee. So you can say employee dot create first, last. Again, this is just a function. So you can say here employee dot create, and you can say, for example, first is first, last is last, age is 10, employee ID is some ID, and this will result in let emp. So static members are attached to types. No surprise there. That's the nature of static members in C#, Java, C++, and so on and so forth. This one is an instance member. So you can say employee dot with name to uppercase and let after changes. So if you look at the body of this method, we are saying this with, and which is nothing but create a copy of this, and this in this case is emp, and change the value of name. So whatever name we have supplied gets changed to uppercase, and a new record value is returned. And this is another example of overriding base classes, interfaces, and so on and so forth. So in this case, this record is implicitly driven from object, so we can override the toString. Nothing special happening here. I have just shown this example to show how you can override from the base classes, interfaces, abstract classes, and whatnot. Don't look at the details of the implementation. It's just whatever the values are available are via string interpolation, those are printed out. Okay, so you can have your record types, and you can have your static members, which are attached to types, and these are instance members, which are attached to the instances. This instance member is an overridden implementation. We want to override the object.toString behavior. Okay, so all right, and there is another thing called anonymous records. Anonymous records is, so if you have to create an employee, you will do something like this. Age is 10, employee ID is whatever. What's wrong? Have I missed something? Yeah, formatting is slightly tricky, but don't bother about that right now. So this is how you create the value for a record which is declared. Now there's something called anonymous records, which is quite similar to anonymous functions. That is, the type may not exist. The type exists in this case, but you want to group values in a record like manner, but without creating the type for one-off cases, for rare occurrences, and so on and so forth. So you can do, let me just copy this and let me just simplify this. Name equals to first and last. Let anon record equals to this and this and this. Now there is no record type declared which matches this usage. We don't have any record because we are trying to create an anonymous record. So all you need to do is add these parallel sorry, at these pipes. And what happens now, that this is an anonymous record. In other words, there is no formal type declared. And the type of this is, if you can see, the pipes are here. So you can create records out of thin air, just like you can create functions out of thin air. There has to be no formal body or declaration and whatnot. This is for one-off cases. This is not for very frequent cases. In certain cases, in pipelines, you create anonymous records, but we will discuss the usage of such things when we discuss pipelines and building complex answers to complex cases. So this is what an anonymous record is, right? Oh, just without these pipes, it's just the same method. You just add the pipes to indicate that you are creating an anonymous record, and there has to be the type need not exist. Okay, and there's another example which is more comprehensive. It's something like this: somebody's name, age, address, which has another anonymous record inside it. So you can go down to any level, practically speaking. It's convenient in certain cases. Now comes discriminated unions, and this is a very interesting feature in F#. In fact, a lot of techniques we use in F# are possible only because of discriminated unions. Now, first of all, let me give you a very simple example, and then only we will complicate it. This is a discriminated union. It's written like this: type name equals to pipe, and whatever comes after these pipes, line by line, or pipe separated by lines, or separated by pipes, you can write it like this, or you can spread it over lines. So all these cases, all these lines that you see after the pipe are known as cases. That here is a type which supports multiple cases. In a value of this data type, int or string, you may have an integer in the I case or a string in the S case. So you may say let v1, which is of type, I'm forcing type so that you can see what's going on. You don't need to really mention the type name, I1, and this becomes so I'm just getting rid of these types because the types are inferred by the compiler, nothing fancy here. S is a case of int to string, I is a case of int or string, not to string or string. So v1 you can see is int or string. Similarly, v2 is also int or string. Now, discriminated unions are used in a variety of ways, but the principal idea is very same. Here is a type which will have cases. Each case has a name, which also becomes a function for you to create values of those types. So I and S are functions as well as cases, case names, however you wish to look at it. A type, cases, each case has a name and a type of value that you are going to put in the value in that particular case. Now, the description I have given on the blog is that discriminated unions are a combination of what I feel C-style enums and unions. So if you know C-style enums, those are enums, those are just cases. Monday to Sunday, or Jan to Feb, or payment method, enums, unique values, identification. And then you have unions in C, which is a structure which holds different pieces of data in different cases. And this is a combination of those two ideas. This is where it becomes exceptionally powerful, okay? Now, here is another example that, and I'll just copy it. So we have another discriminated union called day, which is only cases, no data. And then you have another discriminated union called person, which has two cases, non-employee and employee. In case of non-employee, there is only a name. In case of an employee, there is a tuple, name, data type, star, you are invoking a tuple, employee ID, colon string. You can also do something like this. Instead of this kind of definition, you can create a record type employee equals to name of string employee ID of string, and you can do this also. It just doesn't matter. Here you can say string also. You have to spend some time writing some examples. I have given all sorts of examples on the blog to get a feel of various approaches and possibilities that are there. So in a nutshell, what you have to understand is that a discriminated union is a type which will either be, in this case, the value of it, or in this case, depending upon your need. And this solves way too many problems. So for example, it's a very commonly showcased thing. There's online transaction happening on a website, which may happen in 5 different ways. It may be via credit card, it may be via debit card, it may be via okay, I have this example here. Yep. So payment info, cash. If it was cash, if the payment was made in cash, you don't need any special piece of information. If it was done with card, you are saying, okay, I need the card number. If it was done via a check, you are saying, okay, what's the name of the bank, what's the check number, and was the check, was the date and time, sorry, not time, the date written on check. The problem it's solving is that you don't need to, depending upon cases, which is the traditional approach, you have your cases or identifiers somewhere else, and you have your data somewhere else, and then you bind the two by creating more data structures, and so on and so forth. So what discriminated unions do is just unification / merger of different answers into one technique called discriminated unions. Now, how do you, if you are dealing with a data less discriminated union, then D equals to Monday or a D equals to Sunday, it doesn't matter. Now let's take example of this case. So let's say payment info, payment 1 is cash, full stop. Card, if it is a card, sorry, P2, which is a card. Since it's a function, I need to give this card number 1, 2, 3, 4, 5, 6. Bank check. Let P3 equals to check. And then I have to pass in a tuple of this, which is bank name. I don't know, no money bank. Check number 1, 2, 3, 4, 5, 6. And let's say system.date. So you can see the data types of all of these, P1, P2, or P3 is all payment info, payment info, payment info. But in all these cases, you are holding different data. It's not just P1, P2, P3 are identifying different cases. They are identifying different cases, and for each different case, there is a different piece of data associated with it. Okay. I've already talked about construction, that how do you construct, this is how you do construction. and then there is discriminated union with members. So I'll just copy stuff from here to show you how you can have static members, you can override things, and you can do this. So what I'll do is, with this payment info, I'll say static member create cash equals to cash, full stop. If somebody says I need cash, all you're doing is creating a value of cash type, or you can even do this because it's a function call. No, sorry, you can't do that. Now if somebody says create card string card number, nah, and you will say card number. Now this you can replace by payment info dot create card. Not a very useful example, but this is just to show you that you can create the way we created static members, instance members, and overridden instance members for a record type. You can create members for a discriminated union. Now, one thing I just wish to end this conversation with is, and perhaps tell you what I haven't talked about right now, is it's a very, and just to exemplify, let me just write a function, okay? So let's say you have a function called let do something with email string equals to whatever, and because I don't have anything meaningful right now, I'm just returning a unit. Now, and another similarly another function, let do something with student age which is an int. Now the huge problem here is that what this function is saying, that this function does something with email and give me email which is a string. Similarly, this function does something with age which is an int. A big problem which happens nearly all the time to programmers is there is no guarantee that what you are passing in to this function, just because it is string, it's an email. Just because it's an int, it's an age. So imagine somewhere in your code below you have let height equals to 10, let age equals to 20, and you may end up with doing this, because height is also an integer, age, which is supposed to be the parameter for this function, is also an integer. There's no stopping you. There's no compiler in the world which will stop this. This causes too many bugs, okay? Similarly, here, a string, you can pass in anything. You can either accidentally pass in a name, an address, or maliciously you can pass any string which is not an email address. Now there are two parts to this solution. One is simpler one, which I'll talk about right now. The other is a bigger area, which is domain modeling and data modeling and so on and so forth, which is an intense discussion in itself. So maybe it will come later. So one technique which is frequently involved in F# to control these kind of errors is a single case discriminated union. For example, type email equals to email of string. Similarly, type age equals to age of int. Now you see the pipe is not needed for a single case discriminated union. Now here, let me say let age equals to, which age is age 20, and height is height 10. Okay. Now this function should now accept age, and the moment you do that, if you don't pass in age, it will not work. As long as you're passing age, it will work. If you pass in 10, it will not work. If you pass in height, it will not work. So this methodology of single case discriminated unions solve the whole problem of accidentally passing incorrect data. It kind of arrests it to a great extent. However, a big problem which remains is something like this. Sorry. Yeah. Now what's stopping? So, if it was something like this, a@b.com, everything is fine and dandy. But there is no stopping from calling email case constructor or function with this or with any string. And that's where data modeling techniques in F# come into picture, and we try and arrest this to a greater extent. That requires number of techniques, so I'll discuss it later. But you can still start with single case discriminated unions and bring some sense to your data types, right? Like always, please make sure to visit the blog, check out all the comments that I have placed, and see you in the next one. Thank you. Bye-bye.